Hello everyone. Let's analyze. So today we're going to talk about the inverse function theorem, specifically about functions that map vectors in Rn to vectors in Rn. But before we get into that, let's review the ideas in one dimension. So let's consider the graph of a function y equals f of x. Then to graph its inverse, we essentially take the function and reflect it over a 45-degree line as such. So there we have the inverse of the blue curve. So if y naught equals f of x naught, then x naught equals f inverse of y naught. Furthermore, there's a relationship between the derivative of f here and the derivative of f inverse here. Specifically, because they're reflections, the inverses are reciprocals. In other words, if I'm invertible here, the slope of this tangent line is f prime of x naught. The slope of this tangent magenta line is 1 over the slope of this. It's the reciprocal of this slope, right? Or the multiplicative inverse. Now, of course, if this slope were 0, we'd be in trouble, because then this slope would be vertical. And of course, that would mean that the derivative is undefined. Let's take a look at another example. All right, so here we have a graph of the function sine of x. Of course, you know that its inverse is arcsine, but of course, arcsine can't be defined everywhere, because if I just take my sine function and reflect it across a 45, I get this red curve. But of course, this red curve, if I have no restrictions, is not a function, right? We can see it clearly fails the vertical line test, for example. In fact, it fails the vertical line test of the y-axis. Right? We can't have 0 get mapped to different values. So we have to restrict it to the area that is a 1-to-1 map. So between negative pi over 2 and pi over 2, right, I get a 1-to-1 map. And notice that in the open interval, negative pi over 2 to pi over 2, the derivative of sine is not 0, right? So sine's continuous. There's a 1-to-1 mapping. It's differentiable. I can invert in that interval. So let's remember these lessons, these concepts, and these ideas as we venture into multidimensional territory. So here we have the inverse function theorem in multidimensional space. Suppose f maps an open set in Rn to Rn and is of class Cp. In other words, it's p times continuously differentiable. And the derivative, right, remember that at x naught, the derivative at x naught is a matrix. So that matrix is invertible. Then there exists an open subset within the domain A that contains x naught, so that f on this open subset U is invertible. And the inverse function is also of class Cp, right, which makes sense, because if we think about taking that graph, however smooth that graph is, reflecting it across a 45, we shouldn't lose any smoothness. The derivative of the inverse at y, defined to be f of x, is given by the inverse of the derivative at x. Right, and of course, the inverse for matrices is a multiplicative inverse, right? So it's the analog for a reciprocal. So this should make sense, right, by taking the ideas from the one-dimensional case and applying it to the multidimensional case. So just a quick note, when I say that the derivative of f at x naught is invertible, that's a matrix. And when I say that matrix is invertible, right, that's equivalent to saying that the determinant is not 0. So that's an equivalent way of interpreting that constraint in the hypothesis. So the proof of this has a few steps. But again, our concepts from one dimension apply here. We just have to be careful of how we apply it in multidimensional space. So first, before we prove it, let's give kind of a bird's eye view of the path we're going to take, and then we'll prove each idea along the path. So let's give an outline of the proof. So let's prove the theorem when x naught is 0, f of x naught is 0, and the derivative is the identity. So if we think in one dimensions, we're going to prove this for the case where the graph passes through the origin and the slope of that graph at the origin is 1. So how do we prove the theorem? Well, to prove invertibility, we have to prove that for any y in some neighborhood of 0, there's a unique x such that f of x equals y. And we're going to do it by using a potent combination of the continuity of f, the mean value theorem, and contraction mapping to argue that gy of x, which is defined to be x minus f of x minus y, has a unique fixed point in some ball centered at 0 with some radius delta 1. Right, that's how we're going to get to this. For each y, there's a unique x such that f of x equals y. We're going to use the debris of the previous machinery to show that the inverse is continuous. We're going to show that the inverse is differentiable by asserting the CP class of f and the fact that the set of all n by n non-singular matrices within n by n is open. Then I'm going to show that f inverse is class CP by an induction step, invoking the class of f, and the fact that the inverse function, right, the function that maps a matrix to its inverse, is continuous. Then, once we prove this kind of more simple case, we'll prove the generous case. If the derivative is not the identity, then we just scale it by multiplying f of x by the inverse of the derivative. Right? This inverse here doesn't change with respect to x, so it's treated like a constant. So the derivative of g is just this matrix times the derivative of f. And so at x naught I just get the identity, which means g satisfies all of the simple condition above. And if x naught is not 0, then we'll just shift, right? We'll shift so that our new shifted function is 0 at 0. And therefore, it satisfies the case of the simple condition. And then if h is invertible, then so is f, using this formula. So let's begin our adventure. Okay, so let's consider the simple case that x naught is 0, f of x naught is 0, and the derivative is the identity. Again, this is kind of analogous to a one-dimensional case where the graph passes through the origin with a slope of 1. Our goal is that for each y in some open set containing f of x naught, of course f of x naught is 0, there's a unique x for which f of x equals y. Because if for each y there's a unique x, that mapping is the inverse function. So let's define g of x to be x minus f of x. Of course, g of x is class CP because, well, the function x is c infinity and f we've assumed to be of class CP. that means that the derivative of g is continuous, because I can take p derivatives and retain continuity. Note that the derivative of g at 0 is the identity minus the derivative of f at 0. Of course, the derivative of f at 0 is the identity, so the derivative of g is 0. Furthermore, g of 0 equals 0 minus 0, which equals 0. Now, since the derivative of g is continuous, right, we know what that means. We have a definition for it. There exists a positive delta, we'll call it delta 1, so that if x is within delta 1 of 0, the derivative of g at x minus the derivative of g at 0 is less than 1 over 2n, right, the norm of that distance between them. And of course, right, that's true for each entry of g. Right, g is, right, can be thought of as a list of functions because g is vector valued. So in other words, if x is in an open ball centered at 0 with radius delta 1, and of course this condition and this condition are the same, we're just using different notation to say the same thing, then the derivative of the ith entry of g, remember this is 0 because the derivative of g at 0 is 0, which is equal to the gradient, because remember the derivative of gi is the gradient transpose. And of course the transpose doesn't affect the norm, and so we're only considering here the norm. So the norm of the gradient of gi is less than 1 over 2n. So this statement and this statement are equivalent. So the mean value theorem implies there exists a list of vectors in the open line containing or connecting 0 and x. And because x is in a ball centered at 0 with radius delta 1, then so is that open line containing 0 to x, and therefore so are all these vectors c1 through cn. And the mean value theorem tells us that gi of x, which equals gi of x minus gi of 0, because gi of 0 is 0. Remember, g of 0 equals 0. So the mean value theorem tells us this equals the derivative of gi of ci times x minus 0. And the derivative of gi is just the gradient transpose times x. So we get gi of x equals the gradient of gi transpose x, where the gradient is evaluated at some ci. Now here we're going to use the fact that the 2 norm of a vector is less than or equal to the 1 norm of a vector. I would encourage you to prove that to yourself. Just for some arbitrary vector in Rn, the 2 norm is always less than or equal to the 1 norm. Well, the 1 norm is equal to the sum of the absolute value of each entry of g summed. And well, gi of x is equal to the gradient transpose times x. And here we can use the Schwartz, the Cauchy-Schwartz, to write this is less than or equal to the norm of gi times the norm of x. Now the norm of x is less than delta 1, because remember I'm inside of a delta 1 ball. And the norm of the gradient is less than 1 over 2n. All right, we proved that here. Therefore, the norm of g is less than or equal to the norm of x divided by 2, which is less than delta 1 over 2. Since g is continuous, we can also close this set. G maps the closed ball of radius delta 1 to the closed ball of radius delta 1 over 2. Now, remember, our goal is to work towards building a contraction, right? That's how we're going to get there exists a unique x for each y, right? Because a contraction has a unique fixed point, right? So that's what we're working towards. So we're going to define gy of x to be y plus g of x, which is y plus x minus f of x. So hopefully we can see that if gy of x has for a given y has a unique fixed point, that would imply x equals y plus x minus f of x, meaning y equals f of x, and that x is unique. It's the unique fixed point. So let x be in this closed ball. The norm of gy of x is the norm of y plus g of x. Use our triangle inequality. That's less than delta 1 so long as the norm of y is less than delta 1, because we know that this is already less than delta 1 over 2. All right, so we need the norm of y to be actually less than delta 1 over 2 as well. So we get delta 1 over 2 plus delta 1 over 2 if this is true. This shows that the mapping of gy, right, from x in here gives me an outcome of a vector inside of the same set, right? That's one of the conditions for a contraction, that it maps a closed metric space to a closed metric space. Now suppose x1 and x2 are in this closed vector space. Then gy of x1 minus gy of x2 equals, well, by definition, y plus g of x1 minus y minus g of x2. Of course, y minus y cancel. I get g of x1 minus g of x2. By applying the same mean value theorem machinery, that's less than or equal to this sum of the norm of gi, the gradient of gi, ci, times x1 minus x2. And again, these are each less than 1 over 2n. I'm adding n of them, so I get half times this. So I get gy of x1 minus gy of x2 is less than or equal to half times this, which implies that gy is a contraction. Because gy is a contraction, and it's defined in terms of y, for each y, right, specifically each y in this set, there's a contraction, there's a unique x such that x equals y plus x minus f of x. If I subtract x from both sides, I get that y equals f of x, and the x is the unique fixed point, meaning x equals f inverse y is well defined. Furthermore, the inverse maps the closed ball of radius half of delta 1 to the closed ball of radius delta 1. So we've proven that, in fact, f is invertible on a subset. Now let's use what we've derived to show that f inverse is continuous. Okay, so let's use what we've derived to show that the inverse is continuous. As you might imagine, we're going to start with let epsilon be greater than 0. Suppose y1 minus y2 is less than half of epsilon, and that y1 and y2 are both in the closed ball of radius delta 1 over 2. Well, if x1 is f inverse of y1, and of course we're guaranteed that there's a unique x1 for that y1, and x2 is f inverse of y2, we know that the inverse maps the ball of half a delta 1 radius to the ball of a full delta 1 radius. So we know x1 and x2 are both in the ball of radius delta 1. Therefore, the inverse of y1 minus f inverse of y2 is the norm of x1 minus x2. That's g of y1 of x1, because remember x1 is a fixed point of this gy1 map, minus gy2 of x2. Again, using the fact that these x1s are fixed points of the gy1. Then using the definition of what these are equal to, this is y1 plus g of x1 minus y2 minus g of x2. We use our triangle inequality. We know already that this is less than epsilon over 2. We know that this is 1/2 x1 minus x2. How do we know that? Well, because we know that g had that Lipschitz continuity condition. And remember that x1 minus x2 is equal to this, which is kind of where we started. So I can take this and subtract it from both sides. If I take this term, subtract it from both sides, and multiply by 2, I get this condition. So therefore, the inverse is not only continuous, it's actually Lipschitz continuous. And I get less than epsilon. Thus, F inverse is uniformly continuous in this closed ball. Now our next step is to prove that F inverse is differentiable and that the derivative at y, which is equal to f of x, is equal to the derivative of f of x inverse. So what do we know? Well, we're assuming that the derivative of f at x naught is the identity, that the derivative as a function of a is continuous, right, because f is class Cp, which means the derivative of f is class C p minus 1. There exists a delta 2 for which the derivative of f of x is invertible for any x within delta 2 of 0. In other words, if df of 0 is invertible and x moves a little bit, then the derivative of f of x should still be invertible. Right, that comes from the fact that the set of non-singular matrices is an open subset of the set of all square matrices. So let delta be whichever is smaller of delta 1 and delta 2. Suppose y1 and y2 are both within half of delta of 0. And x1 is f inverse of y2, and x2 is f inverse of y2. And given this condition, we're guaranteed that these are well-defined vectors. So if I'm going to claim that the derivative of this is given by this, I need to show that this goes to 0 as y1 heads to y2. Now remember, f inverse of y1, f inverse of y2, that's x1 and x2, y1 and y2, f of x1 minus f of x2. I can take this matrix and factor it out. So I'll just get the derivative of f at x2 times this, plus this. And here I'm multiplying by 1. Now notice I switched these denominators. I factored out this, and then used the properties of matrix norms to get this inequality. I just rewrote this. x1 is f inverse of y1, x2 is f inverse of y2. By the way, this term right here is less than or equal to 2 because f inverse is Lipschitz continuous. So in other words, this is bounded above. This is some number bounded above and bounded below. So I have this 2 term come over here. Now this goes to 0 as x1 goes to x2 because I know that f is differentiable at x2. And so the meaning of differentiability is that this goes to 0 as x1 goes to x2. Now, as x1 goes to x2, that means y1 goes to y2. So this still goes to 0 as y1 goes to y2, which is exactly what we wanted to prove about this. Therefore, the inverse function is differentiable on a preimage of b of delta over 2. And the derivative at y is given by the inverse of the derivative of f at x, where x is f inverse of y. So we've proven our objective for step C. Now we need to show that the inverse function is class CP. What do we know? We know that f inverse is continuous. We've proven that. We know that the derivative of f is continuous because f is class CP, which means the derivative is class CP minus 1. We know that the inverse function, the function that maps a matrix to its inverse, is continuous. By the way, how do we know that? What's the idea behind it? Well, the inverse of a matrix is a polynomial of a matrix. We can show that by saying if P is the characteristic polynomial of A, then P of A is 0. And since P of A is a polynomial, this 0th order term is in fact just the determinant of A, and the determinant of A is not 0. The determinant of A is not 0 because we're assuming that A is non-singular. Therefore, if I solve for A and if I solve for the identity and factor out A, I get an expression for the inverse. So the inverse of A is a polynomial, and furthermore, the coefficients of that polynomial depend continuously on A. So let's consider what the derivative of f inverse is. The derivative of f inverse is the inverse of the derivative of f evaluated at f inverse of the argument. So for example, the derivative of f inverse of y is the inverse of the derivative of f at x, where x equals f inverse of y. So in fact, this expression here is the function that represents the derivative of f inverse. And it maps vectors in a delta over 2 radius of 0 to n by n non-singular matrices. Now we also know that f inverse is at least C1. We know that. In other words, we know that f inverse is differentiable and its derivative is continuous. So remember, df inverse of y is equal to this composition of functions. We know that this is C1, we know that this is Cp minus 1, and we know that this is C infinity. That means df inverse is C1, right? It's right the kind of the least order of this. And if df inverse is C1, f inverse is C2. So we knew f inverse is C1, now we know it's C2. So let's repeat the same argument, but now we can say that f inverse is C2. Well, if f inverse is C2, and that's the least of these orders, then the derivative of f inverse is C2. And if it's C2, f inverse is C3. And we can carry out that argument to show that the derivative of f inverse is Cp minus 1, meaning f inverse is Cp. And of course we have to stop there because that's as far as we know about this continuity. That f is Cp, which means the derivative of f is Cp minus 1. So these are both kind of the same order. So we can't go any further. But we've proven that f inverse is not only continuous, it's of the same class as f. Again, which makes sense if we think of the inverse as a sort of reflection. Now, what if we're not in the simple case? What if x naught is not 0? What if f of x naught is not 0, and or the derivative of f at x naught is not the identity? Well, suppose that the derivative of f at x naught is t, and t is not the identity, but it is invertible because that's in the hypothesis of our theorem. Well, let g of x be essentially a scaling of f, where that scaling is a linear mapping. It's t inverse times f of x. But t inverse doesn't depend on x. So the derivative of g at x naught is t inverse times the derivative of f at x naught. But the derivative of f at x naught is t. So the derivative of g at x naught is the identity. Well, then we have essentially the previous condition. We're assuming here, right, we're only assuming that this has changed, so x naught is still 0. So now we're in the case that we've proven. Therefore, g inverse exists, and I can define f inverse as the composition of g inverse and t inverse. And that works because if x is equal to g inverse of t inverse times y, I could take g of both sides. I get g of x is t inverse of y, right? Because g of g inverse is an identity mapping. Now, g of x is by definition, right, by construction, t inverse of f. So if I multiply both sides by t, I get f of x is equal to y. So if only this has changed, right, we still can keep all of our results. Now let's consider the case that this has changed. Right, so x naught is not necessarily 0, and f of x naught is not necessarily 0. Well, then we just shift. We shift the argument, and we shift vertically. Therefore, h of x has all of the pretty properties. H of 0 equals 0. Since h of 0 equals 0, and the derivative of h can be expressed in terms of the derivative of f, which has all the properties we need, I know that h inverse exists in an open neighborhood of 0. And I can construct f inverse in terms of h inverse, specifically using this formulation. And that works because if x is h inverse of y minus f of x naught plus x naught, then I can subtract x naught from both sides. I get this. I can apply h to both sides. H of x minus x naught equals, well, by definition of what h is, f of x naught plus x minus x naught, so just f of x minus f of x naught. F of x is y minus f of x naught. That implies, of course, that f of x is equal to y. So let's work out an example. Let's consider this function u of x equals e to the x1 cosine of x2, e to the x1 sine of x2. Now you might recognize that this function that maps R2 to R2 is equivalent to the mapping e to the z, where z is a complex number. So let's show that this function is locally invertible near every point, but not globally invertible. Furthermore, let's give an expression for the derivative of the inverse. Well, it's clear that I can take as many derivatives in any direction I want, so it's clear that u is class C infinity. Right, so I can take a derivative. Right, I can get the derivative by computing this Jacobian matrix. I'll get e to the x1 times cosine of x2, negative e to the x1 times sine of x2, e to the x1 times sine of x2, e to the x1 times cosine of x2. And the derivative of this matrix, in other words, I want to know, is this invertible? where the derivative is e to the 2x1 times cosine squared plus sine squared of x2. Cosine squared plus sine squared is 1. So get e to the 2x1, and e to the 2x1 is never 0. Never ever. So because e to the 2x1 is never 0, this matrix is invertible for every x. Therefore, I can apply the inverse function theorem. Right? Every x satisfies the conditions of the inverse function theorem, so therefore this function is locally invertible near every point. Now, because it's invertible at every single point doesn't make it globally invertible. Furthermore, what's the derivative? If y equals u of x, the derivative of the inverse at y is given by essentially the inverse of this matrix, which is 1 over the determinant times flip these entries, flip the sign on these entries, given by that. Which if I multiply through is equal to this. Now, the idea about not being globally invertible, well, u of x plus 2 pi e2 is u of x, so that nixes any idea of any kind of global invertibility. So hopefully you might recognize how the result of this problem has some implications of a complex defined log function, since u is equivalent to a e to the z, where z is a complex number. Well, that's all for today.